This screencast is going to show the derivation of the negative binomial distribution, and then I'm going to cover an example of its use. The negative binomial distribution is related to the binomial distribution, but there are some important differences. A binomial distribution, we are looking at a fixed number of trials. The negative binomial distribution is a little bit different in that we are looking at a fixed number of successes, and what we're trying to do is answer the following question. What is the probability that it will take us X trials to reach our R successes? And remember that this is provided. So that's what we're trying to answer with the negative binomial distribution. So we can write this as we have a bunch of different trials. Now the last one is always going to be a success, okay? Because we're asking, what's the probability that it will take us X number of trials in order for us to finally reach those R successes? And somewhere along in here, we're going to have other successes. The total number of items that we have is X. So we have X number of trials. Now, the total number of trials excluding that last success would be X minus 1. If we have R successes and we have X trials, that means that we will always have X minus R failures. And those X minus R failures are going to be in the first part here before the last success. So to create an equation where we can calculate the probability that it will take us X trials to reach R successes, we're going to do the following analysis. So the left-hand side here, everything before our final success, that includes R minus 1 successes because we have a total of R successes. The last trial is always going to be a success. And we have X minus 1 spots to put those R minus 1 successes. So how many ways can we put R minus 1 successes into X minus 1 spots? Well, that's simply a combination. So we have X minus 1 spots, and how many ways can we put R minus 1 successes? Now, in order to calculate the total probability of those number of successes into X minus 1 spots, we have to take each one of those arrangements, because this is going to be the number of arrangements that we're making. For each of those arrangements, we have to multiply by the probability of any of a single arrangement. So what's the probability that we will have a arrangement that includes R successes, because we're looking at the total possibilities now, and X minus R failures? Well, we're going to look at the failures first. So the probability of a failure is 1 minus the probability of success. We have X minus R failures. And then we multiply that by the probability of success times R successes. Again, the reason we are doing this is because we have the probability of R minus 1 successes, but we also have another success, so that's why we multiply by R and not R minus 1, but the number of ways is going to be R minus 1 successes because we're constraining that last trial to be a success. So the probability that it will take us X number of trials to reach R successes is given by the following. It's also important to note that X must always be greater than or equal to the number of successes. So I've got an example problem here. Your little sister is selling Girl Scout cookies. She's going around house to house until she sells all 5 boxes. What is the probability that she finishes selling them by the 8th house? So we have a fixed number of successes. The number of successes is 5. There's one thing I left out here, and that is the probability that any one house decides to buy a box of Thin Mints is 30%. She could get really lucky, and in 5 houses, she could sell all 5 boxes. Or she could sell them on the 6th house, or the 7th, or the 8th. So really, This is sort of an at least problem, or you have multiple possibilities. So if we sum up the probability that you'll finish selling them on the 5th, 6th, 7th, and 8th houses, that's going to answer our question of buy the 8th house. So I'm just going to write this for the first for x equals 5. So f of 5, I'm just plugging these values of x equals 5 and r is 5. So I plug those along with the probability of success into the negative binomial distribution equation. So to answer the question, we would do f of 5 plus f of 6 plus f of 7 and f of 8. And if you do this, you end up with about... I'm going to show you how to do this in Microsoft Excel, because Microsoft Excel has a really nice negative binomial distribution function. So I'm over here in Microsoft Excel. I've put a cell here for the probability of success. I'm going to name that P up here in the name box. We want 5 successes, so I'm going to name that R. Oops, in Microsoft Excel we can't name things R, so I'm just going to call that RR. Now we're going to put in what is the probability that we will have 5 successes exactly by the 5th house. So this is going to be neg binom.dist. That's a built-in function. So we have the number of failures. The number of failures here is just always going to be x minus 5. Okay, not minus the x. So that's going to be the number of failures. For the first one, when x is equal to 5, that means we have 0 failures. Okay, the number of successes will just be our x. The probability of a success is our p. And the cumulative here, I'm going to put in false. And another thing, let me just go back here, and instead of this 5, I'm just going to put in RR, because that is our required number of successes. The reason I'm doing that is I can always update this spreadsheet later on if I want to do 6 successes or 7 and so on. Okay, so we put in false because we don't want it to be cumulative. So that's the probability that we will sell all 5 boxes at exactly the 5th house. Now I can drag this down. This will be what's the probability that we sell out exactly on the 6th house, on the 7th house, on the 8th house. I did make one error in the number of successes here. Instead of being B6, that's not the number of trials, this is the number of successes, and that should be RR. So a negative binom dist, we have the number of trials minus the number of successes. That equals the number of total failures, number of F. Then we have number of successes is going to be our R here. We have a probability of success of 0.3, and I don't want it to be cumulative. So that's the probability we'll have exactly 5 successes by the 5th trial. I copy this down, and I keep going. If I sum all of these, then that gives me the probability that I will sell out by the 8th house. So let me just explain one more thing. You may have been wondering why I used false. So false again is we would sell it at exactly the 5th house, exactly the 6th, 7th. But if I want to do a cumulative, which is sort of what this question is asking, I can always change this to be true. So that's up through the 5th house, what's the probability that we will have sold out? And you can't have, for the negative binomial, you can't have 4, 3, 2 houses because x always has to be greater than or equal to r. But now I can copy this down, and this tells us the cumulative probability. So up through the 6th house, up through the 7th. And we see that we get the same thing as we did before when we just summed everything. This is the probability that by the 10th house we will have sold all 5 boxes of cookies.